Okay, hello everyone. Welcome to another episode of History of Science and Technology Q&A. And I'm happy to try and answer questions about either history of science and technology in times where I've personally been involved, or from distant past where I might have researched certain areas of history and be able to talk about them. So we have a number of questions saved up from previous times. There's one here from Binary saying, what sort of math was ancient India up to? I don't know all those details. I will say a few things about the history of, for example, Indian mathematics, to some extent also Chinese mathematics, but particularly Indian mathematics. One of the challenges in history from that part of the world is, well, in history, Greek, Roman, those kinds of periods, things got dated. You kind of know this was in the, the system of dates often, at least in the Roman Empire, was, it tended to be the nth year of so-and-so's, of Emperor so-and-so's reign or whatever. There was so-called regnal dates, were the usual way of stating dates for things. And eventually we're going to have those in Wolfram Alpha. We still don't quite have those yet. But things, a lot of things got dated, so you know when they're from. It tended to be the case in Indian traditions that there would be some document, something, not really document, because the original documents are never preserved. There are always copies of copies of copies, but there will be some, Ushbanipad or whatever thing, or whatever it is, which had been passed down through many generations, but it didn't come with a date. So you don't really know when it was from. So that's one of the challenges is, and it could be off by 500 years sometimes. Another thing is that it's always a challenge to take a modern version of some set of ideas and try and connect them with a much older, quite different sort of paradigmatic framework and quite different presentational framework in which those ideas were given in the past. So for example, I was looking at something recently. One of the things that was done in ancient India is the development of a kind of systematic grammar for Sanskrit. And there's a person called Panini who developed such a grammar. And I thought, I'm curious to what extent people sort of say, this is a grammar that looks like the modern sort of production rule grammars that we know originated around 1956 for both generative grammar for human languages and grammars for computer languages. I'm curious how similar what Panini wrote for his grammar for Sanskrit was to those production rule grammars. So I fairly recently went back and looked at some of this, and it's really hard to interpret because the grammar is written out as essentially a series of aphorisms. Okay, well, that's not that different from a production rule, but often they're given as things where they are an example, like verbs work this way. Now that's sort of like the production rules we have, where there are kind of pattern variables in the production rule, but it sort of isn't quite like that because it says verbs work this way and it could be this or this or this. And you kind of can infer from that the this or this or this, that there's a piece that's fixed and a piece that changes. And so that's kind of the pattern variable. But you're starting to then have to make inferences about what kind of the cognitive structure that was being described was. And how does that relate to the modern version of production rules? What's the essential aspect of production rules for a modern grammar? How did it compare to what was being done there? Now, it's my impression that I personally tried to understand some of this, like for example, the Fibonacci series. So the origin that we kind of have well nailed down for that is from Leonardo Fibonacci in around 1202, maybe something like that, where Fibonacci was a person in, I guess, Venice primarily. Was it Pisa? I forget. Somewhere in Italy, who oh, it's Pisa actually. Now that I think about it, he one of his big achievements was to bring Hindu Arabic numerals to the West. Before that time, you wrote down a number, it was written down typically in Roman numerals. What Leonardo Fibonacci did was to say, Hindu Arabic numerals are really a better way to do this. He wrote a book called Liber Abaci, the Book of the Abacus. And what he's probably most famous for today was at the very end of that book is this kind of word problem about rabbits. And the word problem about rabbits generates the Fibonacci series, 1, 1, 2, 3, the series that says the nth value is the sum of the n-1th value plus the n-2nd value. And he had a word problem version of that about rabbits and different seasons and reproducing rabbits and so on. But in any case, so that's the origin that we know is Fibonacci, Liber Abaci, the Liber Abaci book. It's well dated. It's kind of been passed down. We kind of know how it originated. But the Fibonacci series is something which, I don't know, I think if the Fibonacci series hadn't been a known thing, I would have discovered it in my life at least 10 times, because it's something that kind of naturally shows up in lots of kinds of problems. And it also naturally showed up in essentially mathematics that was done in ancient India. And in particular, it showed up in the study of prosody. That is the study of kind of how you, when you create a piece of sort of, musical poetry that you set to music, so to speak. There's the question of how you kind of scan the poetry. So for example, I don't know for the Indian case, but in the case of Greek, for example, or Latin, in Greek, there are things like, iambic pentameters and things, which are, the pentameter means the 5 feet in the meter, and it'll be, long, short, short, or something like that. There'll be a bunch of long, short, short, long, short, et cetera, et cetera, et cetera, things that go in a particular line of a poem, just like, I don't know, in English, limericks or something, have a particular way of going, of being structured in that way, I think. But in any case, it was, at least I know for Latin and Greek, it was a kind of a thing that was done, was to have a certain rhythm of the poetry that was based on where are their long vowels, where are their short vowels, and so on. I guess the same thing was done probably in Sanskrit. So the question was asked, well, how many possible forms of the long, short, short, long, et cetera, are there? And the answer to that is Fibonacci numbers. And that was something that apparently was looked at in kind of ancient times in India. Again, I haven't looked at that source material, and it's often challenging to know, somebody might say, in that particular case, it's probably quite easy to decode. It probably says, the number of possible poems is given by, and it'll probably have a word description of something where maybe it gives the recursive formula. I don't know exactly how it works. Maybe it gives examples of the numbers. I'm not sure, again, exactly how it works. But that's probably a fairly easy one to kind of pick out of kind of the ancient works and see, yes, it really is something just like modern Fibonacci. I would say, the effort to figure out, did something get figured out at a certain time in history, and can you tell? I remember a number of years ago, I was visiting the Leibniz archive. Leibniz was a person who had many things to say about kind of the early ideas of computation in the late 1600s. And he had this idea of the characteristica universalis, this kind of universal language for representing things sort of symbolically. And so my kind of slightly joke statement was, let me see if I can look through his manuscripts and see if there's a Turing machine in there. And just as a footnote to this, Leibniz was a person who had written many, he was a bit of a disorganized writer. He discovered many interesting things, among them pieces of calculus, invented the integral sign, lots of kinds of things like that. He also had a lot of ideas about logic and knowledge, and he kind of would have done Wolfram Alpha probably if he'd been 300 years later and had the technology to do it. But Leibniz was a bit disorganized in terms of uh, his way of presenting things, and he uh, he was the and so unlike some other sort of well-known scientists, philosophers, or whatever of old who had very systematic books that they presented things in, Leibniz had, it was much less organized. But anyway, this question of, could I find a Turing machine in the works of Leibniz, some kind of idealization of computation? It's a challenging thing. I think the answer is no, it's not there. But it's hard to know that for sure, because his explanations were not that clear. His, there's a lot of, he has weird little sketches in the margin, and he has all kinds of things where it's written rather obscurely. And did he have the idea or not have the idea? Well, I don't think he had that specific idea. It's, Leibniz himself, I would say that his reputation, Voltaire, I think, kind of made fun of Leibniz and talked about him having talked about, what did he call him? Doctor, what was the name? I forget. Really emphasized Leibniz as the world is the best of all possible worlds type thing, which I'm not sure was quite what he really meant in his kind of philosophical description. I mean, I realized recently with Leibniz, just to give a sense of the difficulty of projecting backwards from modern understanding to what people thought in the past, Leibniz was very big on this idea that somehow the world is made of monads. Things like, I don't know, some modern functional programming languages have picked up the word monad just as something a little bit, as a rather different kind of thing. But Leibniz had this idea of a monad. And for years, I've been trying to figure out what the heck is a Leibniz monad? Because one of the things that he would talk about how sort of the world is made up of monads, and all that matters is kind of the relative positions of monads and so on. And the key thing that just had me totally confused was that, as I understand it from the translations that I've seen of Leibniz, he describes monads as each monad has a consciousness. Well, by the time we're talking about that, it's like, I don't know what on earth that means. We're talking about sort of some kind of atoms in space, atoms of space. Maybe that's somewhat similar to what we've been doing in our physics project, but they each have a consciousness. It's like, help. That's far away from what I understand about how things work. But what I realized recently is when he said that, and I need to go back and look at the original Latin and see whether the translation was what confused that. When he says consciousness, what he means is, I think, they do something, and they do something spontaneously. And in fact, that's bizarrely similar to what we talk about in our current model of physics, where we talk about atoms of space with these connections and rules being applied, and the rules are just doing something, that the rules just get applied. And could be that what Leibniz had in mind when he said every monad has a consciousness is just every monad spontaneously does something. And it could be very much the same kind of thing as every connected collection of atoms of space just does something. So that's a place where, again, this issue about sort of back projecting and interpreting things is quite hard, because Leibniz he didn't have the metaphor of our modern computers where he says you apply a rule, you run a program. He didn't have that metaphor because he didn't have computers. I have to say, I was really struck when I was visiting the Leibniz archive. What Leibniz was sort of tried a practical effort. He made out of brass, he made a 4-function mechanical calculator. And it spent like 30 years trying to debug the thing and get it really to work. And it was really very charming to read his essentially marketing material for this calculator about how it is, it will save lots of time and so on. It's kind of like big sheets of paper with essentially marketing blurbs for the calculator. But it wasn't ever very practical because it was just a difficult piece of engineering, particularly difficult to do carries mechanically, because when you have just one number that you're sort of trying to, one wheel that is representing one position in a positional number, if you carry, then you've got to turn one wheel and it's got to entrain the turning of many other wheels. And that's just mechanically difficult to achieve. And the forces don't work out easily and so on. And Leibniz had lots of trouble with that. But let's see. What I was going to say was that in in the back room, at least when I visited the Leibniz archive, was the brass calculator, and I was realizing in Leibniz's time that was the only computer-like thing he had ever seen. Whereas in today's world, it's like we've got billions of computers. I have to say, as I was thinking about that, as I was looking at that, I was thinking, what will we've got billions of computers, what will that look like or sound like to somebody in the future? And I think the answer is, people will say, well, you only had billions of computers? Now everything is made of computers. In today's world, when we have materials, they are just molecules that are just set up to just sit there as molecules, so to speak, and have various chemical or physical properties or whatever. But I suspect that one of the things when we finally figure out, and I think actually I have some ideas in recent times about this, how to do molecular scale computing, it will be the case that even within those individual molecules, instead of a piece of plastic, you'll have this thing made of molecules where the molecules have essentially are programmable to do computations at a molecular scale. And so to Leibniz, he saw one computer. In today's world, we see, I don't know, in the room I'm in right now, I don't know how many computers there are, some number of tens of computers probably. In the future, my guess is that one will say essentially everything will be made of computers, so to speak. But in any case, I think the original question that was asked was about math in ancient India, and there are a few other things that I know about that, but I have to say it's a bit sketchy, so I probably shouldn't volunteer the sketchy things I know about that. I will just say that this whole question that comes up is, oh, such and such an idea, was it actually invented by ancient Indian sage X, or was it really invented 1,000 years later by somebody in Italy or something? And you might think that was easy to answer, but it's often not. It's often not in the case of Indian material because of the dating problem. It's often not because it's very hard to tell, was that aphorism that was written down, was that really the essence of the idea that we now understand in this or that way or not? That's a challenging thing to figure out. And sometimes to even have any hope of figuring that out, you have to have a huge amount of context of what was the sort of ambient understanding of things in that time in India and so on. And again, that's a challenging thing. I mean, it reminds me of the problem of some of the things that I've done in science. People say quite often, oh, that resonates with some particular area of kind of Eastern thought. And that's often really challenging for me to decode, almost impossible for me to decode, because, I've grown up in kind of a Western science-oriented tradition, so to speak, which has a certain way of talking about things. And when somebody says, well, this is, they talk about how the world, how there's a soul that is the whole universe and things like this. And that has a very, has probably a very clear meaning if you've sort of grown up in this kind of culture where that's just part of what is discussed. But it's really hard to understand coming from sort of the Western, I don't know, analytical tradition or something. And so I think that that's another thing that kind of bites one in trying to understand, what was understood about, let's say, mathematics at some time thousands of years ago in India, for example. And it's an interesting question whether, for example, there could have been sort of big developments in mathematics that are either lost completely, like there are no written records, or developments where even they are right there, in one's face type thing, but one just doesn't recognize them today. I mean, I think, people will find in, I don't know, in the sort of various, particularly Jewish writings, people will tend to find, oh, there's this amazing numerological coincidence. There's this thing where this, you look at these letters of this and that and the other, and it turns out you come to some conclusion. And it's really hard to tell for many of those things what, is this meaningful? Is this something just coincidental? Is it sort of back projected from what we know today? What's really going on? Or is this in a kind of an intellectual framework that we just don't have anymore today? I mean, it reminds one of the general problem of sort of the interpretation of archaeology. It's like, when you see these stones, what were they for? Well, if they are for something that we do today, then yes, we understand these stones were for this or that. But if they're just stones that, let's say it's an arrowhead, it's carved in a certain way, and it looks just like a modern arrowhead, or we have a continuous chain of kind of development of arrowheads, and we can kind of see how that worked. But if you've just got a few stones arranged in the ground and they go this way or that way, what was this for? Take something like Stonehenge in England, it's a circle of stones. And what exactly was this for? I don't know. I think there are probably progressively better theories for that. But and then there are questions like, were these set of stones set up this way to align with some particular configuration of the sun at the equinox or something like this? Or were they just put that way? In other words, it could be, well, they meant to align it for the equinox, but they were off by 5 degrees. Well, does that actually mean they aligned it for the equinox, or is it just a completely random orientation, which happens to be 5 degrees away from how it should be aligned for the equinox? And that's really hard to tell. And it's the same kind of thing when you see, if you wonder, were there any sort of lost traditions of mathematics, for example, where you see things where sort of things fit together in a certain way, but was that intentional? Was that not intentional? Is that significant? It might be significant in a framework that we don't have anymore. Reminds me of another example of something like that, the Pythagoreans, 5th century BC or so. They had a kind of this, Pythagoras had this kind of, well, probably somewhat peculiar cult-like setup, but he had things about numbers. Like for him, every number had a significance. There was the male, female, I don't remember what all the different meanings for the different numbers were. And so for Pythagoras, he had this thing called the tetractys, which was the fact that 1 plus 2 plus 3, let's see, plus, am I getting this right? 1 plus 2 plus 3 plus 4 is, that is equal to 10. Right, that's the Pythagorean tetractys. And for Pythagoras, that was very significant because each number was had a significance in the world at large. And so that was a statement about something about the world, which to us today just seems nuts. But at that time, there was a framework in which that made sense. Now, that led Pythagoras to be very interested in perfect numbers, for example, numbers which are equal to the sum of their divisors. Perfect numbers have not been particularly important in the general tradition of mathematics as it's come down to us today. Primes, on the other hand, have been very important, but for whatever reason, perfect numbers have not been so important. But Pythagoras, with a different kind of cognitive framework for the significance of numbers, perfect numbers were probably much more important than primes. So it's this whole question about sort of how you contextualize the things you're talking about and what seems significant at a certain time. What does it mean? How do you deduce whether it had significance and so on? I think an interesting question, if you went and, if you could have your impossible to build time machine and go have a conversation with Pythagoras and start talking about math, it could be that 80% of what Pythagoras would say will be math where we say we don't care, it doesn't make any sense with our current interpretation of what numbers are, and so on. And only 20% might be math that has survived and that we care about in the context that we do math today. All right, long answer to that. Let's see. Oh boy, all kinds of questions here. There's a question from ARC. How were modern shipping containers standardized, and what are some of the advantages of optimal standardized packaging? I don't know the specific history of modern shipping containers. It is always interesting the way that standardization happens or doesn't happen. I mean, a famous one is railway gauges. You know, if you're going to, by the time you have a railway with a certain distance between the rails, you're going to make, railway cars that have their wheels that distance apart. And you definitely don't want a situation where, you have part of a country with rails that are some distance apart, another part with rails that are a different distance apart. I mean, it's still the case. It certainly used to be the case. I don't know if it is today, that in different parts of Europe where things are still, land connected, so to speak, there are different gauges of railways. I think in Russia, relative to other places, I think that was the case. And you'd be on a train and they'd have to swap out the kind of the wheel part of the rail cars because it's going to a different gauge of railway. And that's clearly very inconvenient. And so this question of sort of how do you drive standardization, there's certain kinds of things that drive standardization, like the inconvenience and the expense of having to switch out different, rail car kinds of things. I think in the case of, I'm trying to remember, I remember when we were working on Wolfram Alpha, maybe a decade ago now, and putting in information about shipping containers. I remember noting all of the various different standards for shipping containers. I mean, the main point about shipping containers is that it used to be the case that you would kind of load your cargo onto a ship, and somebody would just take the pieces of cargo and put them on the ship. But then people realized it's much more efficient to load everything into a container and then just take the whole container and stick it on the ship. And so modern ships, it's they're remarkable to see, but they're just a giant collection of container bricks all built up. And, when there are a bunch of ships that are having trouble getting their containers loaded and unloaded in today's specific world, but in general, it's a very, impressive kind of almost robotic process. The loading of, unload containers from a ship, put them on train cars, start them going to their destinations and so on. And I think clearly one of the issues is if you're going to put containers on a ship and you want them to fit together properly, you want those containers to all be the same size because you want them to pack perfectly. I mean, it's like saying if you have a bunch of equal rectangles, it's easy to pack the equal rectangles on the plane. But if you start having rectangles of different sizes, you're like, oh, well, we can fit this into this gap here and so on and so on and so on. And it's kind of like you have to do in memory allocation on a computer or something. Do things fit in this gap or not, or whatever else? And it's much more difficult, and you don't have sort of the optimal use of the space. But it's always interesting to see kind of how standardization happens. And occasionally there'll be sort of something will be kind of teetering on two different sides. Will it standardize this way or will it standardize that way? I mean, sometimes standardization is both good for the world and bad for the world. It's good because it makes certain things more streamlined. It's bad because it means that's the way it's going to be for the next X number of hundreds of years until there's a major disruption in the way that technology works, because the cost of a change is so great. And there are things where things have been standardized and the standards are actually a pretty bad idea. I happen to think that about the IEEE floating point standard for arithmetic. But that's what all hardware for computers is built using, and we're stuck with it for the foreseeable future because the cost of change is immense, and there's a giant stack of technology that's been built on top of that. And I'm sure even for the detailed size and shape of shipping containers, I'm sure there's endless, port facilities that have been built very specific to that particular size. And it's all kinds of, and so it becomes, extremely difficult to change. And I kind of wonder sometimes, standards that get set. I mean, I've been involved, well, I've only been directly involved in one standard setting effort, and it was horrifying. And I kind of decided from that, I'm never going to be involved in such a thing again. It was a standard for the way math is rendered on the web, MathML. It was kind of a thing where we had done a lot of work actually developing kind of methods for rendering two-dimensional math and so on. And when people were interested in sort of having a standard for how to do it on the web, I said, well, we've done a lot of work on this. We can contribute this. We're happy to see that be used on the web. And then it's like, well, let's be involved in a standards committee that does this. And that was just a frustrating experience of the wrong things being concluded through pure kind of human politics, having nothing to do with the actual merits of what should be done, so to speak. And I think that is probably very typical of the way certain kinds of standards get made. I mean, at other times, it's kind of a de facto standard where just there is, for example, commercial success of something, and so it becomes a standard for some particular kind of thing. But I would say that in, standards make for efficiency, but standards also make for inflexibility. Let's see. Well, there's a question here. I'm not sure it's completely relevant to this topic, but about math papers, including improving the workflow for math papers, as opposed to writing in LaTeX and reading PDF. Let's talk a little bit about history of that. Okay. So back in the day, even when I was younger, the only way people sort of presented math was they wrote it, hand wrote it. And what happened to it? Well, there are several technologies that kind of developed around that. The first technology was I guess, IBM Selectric typewriters, because usually you have a typewriter, I had a typewriter, and the typewriter, I lived in England, and at the time when I was using a typewriter, I was living in England, and it was a standard QWERTY keyboard with, that typed the standard letters of the English alphabet, so to speak, with a few little hacks on it. Like, for example, my typewriter had no one digit key, because the lowercase L looked like a 1. So that was the thing you typed to get a 1. Various little hacks like that. But basically, it was the standard English alphabet. So now the question was, well, what if you wanted to type an alpha or a lambda or something like this? How would you do that? The technology that developed for that, I think developed by IBM, was this notion of the sort of golf ball typewriter. So in an ordinary typewriter, right, you have, you press the key and there's a lever, and it presses. There's a long piece of metal with a kind of the little font character at the end of it, and that kind of hits through the ribbon, hits the piece of paper at the place where you're currently typing. And for those who don't know this, I think this is going to be one of these things that's eventually lost to time. The notion of a carriage return, right? That was literally the carriage in which the paper was held on this carriage part of a typewriter, and as you typed, every letter you typed, it would move the carriage slightly to the left if you're typing in English, as you move the letter to go further on the right of the piece of paper. And the carriage return was a lever on the side that you would move the lever, and that would release sort of the ratchet that would allow you to move this whole carriage that had the paper on it all the way back to the left, so that you could start typing on the next line again, and hence the carriage return concept. But so the question was, with that kind of, you just got these big all the keys are built into the typewriter. But then the idea was this kind of interchangeable golf ball typewriter idea, where instead of having these long metal sort of prongs that had letters at the end of it. The idea was you have this sort of golf ball thing, and what would happen is the golf ball was close to the ribbon, and the golf ball would turn around to a different orientation to expose a particular letter and then hit the ribbon. And so that was kind of the idea of a way to have sort of a different presentation of letters for the typewriter. And that meant that when you were typing something that didn't just have English letters in it, when you got to the Greek letters, you would undo the latch, pull out the golf ball, put another golf ball in there, and then you'd have to remember, oh, the lambda is the such and such key that you press on the typewriter keyboard, but then it would be using the Greek letter golf ball, and so you get a Greek letter typed on the piece of paper. I do have to tell one story, which just reminds me. People have some questions here about Dick Feynman, and back in the day when I worked at Caltech, the departmental assistant, a woman named Helen Tuck, who is no longer alive, unfortunately, but very, very lively individual. She was the assistant to both Dick Feynman and Murray Gell-Mann, and the departmental assistant, and she would type people's papers. And when I was writing papers, physics papers in the late 1970s at Caltech, Helen was the person who typed those papers for me. And on her, IBM Selectric typewriter with the golf ball thing and the Greek letters and so on. And it's kind of a funny clash of cultures, because I had this paper where it was a calculation of something in QCD, and I had done the calculation a lot with computers. And I had done algebraic calculations with a computer, and that meant that I had all kinds of weird numbers, 342 pi cubed minus 964 or whatever. Somehow in this document, there were just a lot of nines in the document. And my handwriting isn't great. It's not absolutely terrible, but it's not great. But anyway, Helen typed every single 9 in my document. She typed as a G. And I said to her, "Why did you do that?" She said, "Well, these papers, they never have 9s in them." Now, of course, now they think about it, Benford's law, which tells one the typical distribution of first digits and numbers, tells one that 1 is much more common than 9. There's a log distribution of numbers, typically of sort of naturally generated numbers, just by virtue of the fact that if you pick a number sort of independent of size, the ones that fall in the early part of a kind of a exponent of 10 reduced thing, they'll tend to be more with 1s in them. But anyway, now that I realize it, that this was Benford's law bytes plus the kind of culture clash of actually doing computations, algebraic computations with a computer, caused Helen to type all my 9s as Gs. A big nuisance. It was required retyping. Of course, the big technology in those days was that normally, when I had a typewriter, you would just have this ribbon that just had black on it. And then I was very excited at some point when I was a kid, when I got a typewriter that could have a black and red ribbon. And so you would kind of shift, there would be a sort of shift thing you could press that would cause the next letter you type to not hit the black part of the ribbon, but to hit the red part of the ribbon. So you get a red letter, so to speak, on your piece of paper. But anyway, the other big innovation was that in addition to a black ribbon, you could also have a white ribbon. In fact, you could have something where if you had just typed a letter and it was wrong, you would backspace over that letter, and then you would be able to type the white version of that letter there, so that you would cover the black ink that was down on the paper with white kind of, it used to be called the brand name, at least in England, but you could sort of do this by hand. You would have these little sheets. It was called Tipex in British English. I don't know what it was called in the US, where you would take one of these little pieces of kind of white stuff, and you would, it's kind of a white piece of paper which had sort of white essentially white dye on one side, and you would put that in your typewriter where the key would hit, and then instead of it would hit through the black ribbon, it would hit this white thing, which would then put white onto your piece of paper. But it also, there started to be typewriters that would actually have white ribbons in them, so you could do that correction directly without having to get out your little sheet of Tipp-Ex or whatever and put it in the typewriter. In any case, the other technology, if I look at manuscripts of papers that I wrote back in those days, the technologies that I used tended to be a lot of Scotch tape, a lot of these sort of Avery label type things, and a certain amount of whiteout, of where you would get this kind of white paint-like stuff and sort of white out what you've written. But mostly a lot of papers in today's world, I'll type something and then I'll backspace across it, and it's gone. Actually, I tend to try and store bigger pieces that I wrote in some outtakes file and so on. But in any case, just in case I need to go back to them, although they always have change control and all kinds of other stuff in modern times. But in ancient times, when I would write some manuscript, I would end up with more and more and more layers as I would take, some sentence. Oh, I don't like that sentence. I write it out again. I stick the piece of paper on top of the previous one, and so on. So I suspect there are, it's kind of like in ancient manuscripts, you often find things where people have written over and written over and written over something. I'm sure there are early drafts of papers of mine that are now sort of under the Scotch tape, so to speak, from these kind of rather thick, often manuscripts. Oh, and then the other thing, that's right. The other thing I did, when they got too thick, I photocopied them, and then they would be a single sheet again. Okay, anyway, we're talking about math typesetting. Well, what happened when you would write a paper, you would eventually, you would get it typed, and then you would send it into a journal. And in those days, there was real work to be done by journals, because they had to actually take that typewritten thing, and instead of just having camera-ready copy and just photographing it, or rendering it on a photo typesetter or something, instead of that, or just they would have to actually typeset the paper, which means they actually have to get some kind of, well, in really ancient times, it was with individual pieces of lead type, but then it became photolithography, where they would have to take one of these machines that specifies, how you lay out type and so on, and take what was in your typed written version of your paper. So it went from manuscript to typescript, and then to actual printed versions. Well, how was that actually done? Well, there were folks who were typesetters who worked for journals and who got very expert at taking those things that people had typed with a typewriter and maybe added little by hand, pieces to them. And then, what, I'm trying to think, when I first wrote papers, I'm wondering whether I actually hand wrote the formulas when I sent them into journals. I kind of think I might have done. In any case, so the typesetters at journals had to actually decode all of that stuff and turn it into nice type things. Now, one thing that's interesting is that people who did that kind of typesetting they were craftspeople of artisans who were typesetters. They were not math experts particularly. And so it's rather charming that the names of sort of the math characters end up being based on what they look like. Like I remember there are things called fences, and a fence, like an absolute value sign, which is just a vertical bar. I think it's usually called a fence for in typesetting. These were things that were described by their appearance, because that's, if you don't need to know what the math means, that's a much more effective way to know, oh, I'm seeing this in this paper, I want to pick up the fence to put in this place to do the typesetting. So that was kind of the first sort of big thing that journals would do for typesetting. Then the big innovation was when there was computerized typesetting. And I think the first really significant system along those lines was called TROF. And it was part of the early Unix operating system developed at Bell Labs. And there was a thing called nroff and a thing called troff. And they both had a certain sort of description language for representing, this and then a superscript and a subscript and so on and so on and so on. And troff was rendered for a photo typesetting machine. So it would convert from that specification language into the raw code needed for a photo typesetting machine. nroff would do an approximation based on sort of ASCII art of what that would look like as a thing that was to be rendered. And for example, I think Unix documentation, if you look at the man pages under Linux and things like that, I'm pretty sure those are still formatted using nroff. But anyway, so that was a thing. And certainly papers that I wrote starting in about, when was it? Probably, well, I think the documentation for SMP was done in troff. So that was, in fact, it's an interesting question whether I have the original files from that and whether it could be converted to modern notebooks. I don't know. In any case, that was in 1979. So by 1979, I was using troff, and I used that for a bunch of my early papers about cellular automata and complexity and computation and physics and so on. I think meanwhile, at that time, Don Knuth had decided Don has had this project to write his multi-volume Art of Computer Programming. I think he told me recently that about some particular topic, that it wasn't in his 1962 table of contents, so it wasn't going to be in the books. But he started, it's a sort of a remarkable story. He started what was going to be an 8-volume series of books about sort of everything that was known in computer science, started, I think, in 1962, and the first volumes, I think, came out in like 1968. And it's been kind of a lifelong project for Don to do this. I think things kind of went a little bit off the rails when he got to volume 4. And he's been producing these fascicles, little micro pieces of volume 4, and I think it's split into 4A, B, C, and so on. And then it got little fascicles of that, and it's like it's not obvious that the end is not receding faster than things are getting written. But hopefully it'll be in his lifetime he'll get the whole thing written. It's a very remarkable work of scholarship. And he and I do share a lot of interest in sort of the history of ideas and those kinds of things. But as well as a bunch of content about science. And one thing, it's an amusing fact that these things in ternary writing systems, this Knuth-Bendix completion procedure and other features of ternary writing systems, which Don Knuth studied as a matter of theoretical computer science, have become deeply relevant in our physics project to many very practical things. But I digress. In the effort to typeset his Art of Computer Programming, Don got frustrated with existing systems, and so did what many of us do in those kinds of situations and decided to build his own and develop TeX, as well as a thing called Metafont, which is a font design system. And that has become very widely used. And I have to say, when we were first, back 33 years ago now, when we were first releasing Mathematica, one of the things that we had was a TeX form that would convert, which still exists in Wolfram language today, which will convert a mathematical expression into TeX. And Don had at the time said, TeX is small enough and clean enough. There are no bugs in TeX. And he had this kind of, I think, exponentially increasing bug bounty he was paying out. And I was like, I don't think you want us to send you these things, because as soon as we started machine generating TeX, there were boatloads of bugs, because the TeX interpreter had never seen machine generated TeX. It had only seen TeX written by humans. But anyway, the thing that that sort of TeX became a standard for kind of, if you know what the math is supposed to look like, here's how you can say what it should be. A different problem is, what if the math is supposed to mean something? what about if that x superscript 2 is supposed to mean x squared? What's the relationship between meaningful math and appearance math? And sometimes there might be two things that mean the same thing, but look different, two things that look different that mean the same thing, and so on. The question is there sort of a way, can you make math that both sort of looks like traditional math and means the thing you expect it to mean? So in the mid-1990s, we did a lot of work on that in version 3 of Mathematica to build kind of a two-dimensional typesetting system where you can both enter the input in a way that is two-dimensional and have it mean something. And so what we ended up with was a kind of two branches. We ended up with what we call standard form and what we call traditional form. And standard form is something which has the general appearance of math with subscripts and superscripts and built-up fractions and matrices that are laid out in grids with parens around them and things like that. But it has the feature that every element of standard form is directly parsable and meaningful. In traditional computer languages, they're one-dimensional kinds of things where you just have a string of characters and you break them up with, into in a hierarchical way. But in our starting in version 3 in Wolfram language, you can have two-dimensional syntax where you are parsing the fact that it's an x superscript 2 and that means x squared. And there's some tricky things there. Like, for example, one problem was when you do an integral, you have, integral, okay, that's fine, the integrand, and then you say dx. What's that d? Is it like a traditional communal garden d that you type on a keyboard? Well, no, that's very hard to parse. It's very hard to make that unambiguous. If you start having things like, let's do the integral of d to the d dd. Well, that gets really hard to understand. And so what we invented was this thing we call differential d, which is a different character from an ordinary d. It's typed as escape dd escape in the language. That is something which is then perfectly parsable. You've got the integral sign, you've got the integrand, you've got the differential d, which is an operator, just like plus is an operator, and that's then a perfectly parsable unit. And we had to do the same thing with imaginary I and so on. So that was, and we represent them as some kind of double struct version of a d, and it looks sort of visually very close to what you would see in a sort of standard math presentation of something, but it is uniquely parsable and understandable. I was very amused actually looking at Leibniz's documents that I found, oh gosh, what was it? It was one character that we had invented quite independently as our way of showing that this was a meaningful character rather than just a letter. And he had done the same thing, although it was lost in standard mathematical notation in the intervening years. But in any case, so we had this one branch, which is standard form, where the idea, we have this one branch, which is standard form, where the idea is there may be some interpretations like the differential d and other kinds of things like that, but it kind of looks roughly, it has the spirit of standard two-dimensional math, but it is perfectly parsable. And then we have traditional form, which is as close as possible to what you would see in a textbook, with heuristics about the ordering of polynomials and who knows what else that are sort of textbook style, but it's sort of heuristically arranged that way, but to parse it is not something you can guarantee to be able to do, because there will be things there, like if you say sine to the -1 x, does that mean an inverse sine, an arc sine, or does that mean sine to the -1, just a thing called sine, S-I-N, that happens to be, that's 1 over it, and that's what it means to the power -1, and so on. So it's a more heuristic parsing process, and we represent that in a notebook by having a sort of jagged line on the cell bracket that kind of means warning, danger, this is not so easy to interpret. But actually, this question of sort of natural math understanding, kind of like natural language understanding, how do you take sort of math that people just type that they understand it? Well, we do a lot of that in Wolfram Alpha, of taking things where people just sort of splurt out math notation and they don't really tell you what it means. And just like they splurt out natural language, and you have to kind of sort of work backwards to figure out what it means. And often you can do that. I think one of the things that I found interesting, if you have sort of math where you don't know what it means, can you typeset it? And one of the things that's interesting there is a lot of what makes math typesetting elegant or not is the precise spacing around operators. When you have a circle plus or a union or a this, that, or the other, how much space is there around that operator? Are all the operands really squashed up around it, or does it have a lot of breathing room? Well, and another question is, when you type things in, if I type A circle plus B circle times C, how does that parse? Does it parse as the B circle times C is its own sort of parenthesized unit, and then the A plus is outside that, just like standard order of operations for plus and times, or does it work differently? So one of the things I was curious about, this is in the mid-1990s, I hadn't thought about this in a long time, was when people use mathematical notation like circle plus circle times, or they use more exotic co-product symbols or whatever else, what precedence do they think the operators have? In other words, do they have in their mind something which has where they are supposing that the circle times binds tighter than the circle plus and things like this? So I spent a whole bunch of time looking through all kinds of math books and so on, and mathematical logic is the area with the most exotic notation, at least at the time it was. I think there have been some areas of mathematics that have grown up since then that have at least equally exotic notation, although perhaps there are areas where mathematics is kind of rapidly approaching the kind of logic or computation point. But in any case, what I found, which surprised me quite a bit, was people are remarkably consistent. Even when these operators mean utterly different things, they're remarkably consistent in thinking that the circle times operator binds tighter than the circle plus operator and so on. And also that there's a strange correlation between the amount of breathing space left around operators and the tightness of their binding. So we made use of that to be able to let people type in essentially semantically meaningless stuff, but syntactically parsable stuff, starting in version 3 of Wolfram language. And it's something that I use with some frequency. It's a useful thing to be able to use something which notationally looks nice and compact because it has things like circle times in it and so on, but you can then define your own meaning for it. Okay, so that was the story of kind of making math meaningful, making typeset math meaningful. By the way, I would say that when people were doing back to sort of manual typesetting and for papers and things, I think people used to call that penalty copy when they had to do math. Because, when you're just putting a piece of text and you're typesetting the text, you're like typing out the text and it's all appearing in a nicely organized way. But when you're dealing with math, oh, it's such a pain. You've got to move things around and so on. It was called penalty copy because it was copy, as in textual material, that was like really hard to deal with. And so it was going to cost more, et cetera, et cetera, et cetera. And I think sometimes when people, they probably still do this. It's what I get for not publishing in academic journals for forever and ever. I don't really know these things anymore. But it used to be the case that one of the models for particularly professional societies was this notion of you pay to publish your paper and you pay page charges, and they would sometimes compute those page charges on the basis of, how many lines of text versus how many lines of math. They probably still do that. I have no idea. That probably, even though today it's all computerized and it doesn't really cost anything different, it's probably a revenue generation scheme or something. I should say, back to typesetting in journals, the American Math Society adopted kind of tech pretty early, but other places were less fast to adopt some of these things. And I remember Reviews of Modern Physics, nice journal from the American Physical Society, I think, I wrote a big paper for that about cellular automata. That was in 1983, I guess. And it was interesting because my paper was the first one that was sent to them in TROF in electronic form for sort of automatic typesetting. And actually, in a way, although it was in some ways good because I had some kind of unusual, unexpected physics notation, so to speak, in that paper that probably would have had many iterations going backwards and forwards, correcting proofs if it had been done not directly in electronic form. But it did have the feature that I think it was more difficult for them to like size pictures correctly in the paper and things like that, because it was presented in TROF. And there were many pieces of back and forth about the electronic version of that. But I was kind of I kind of led in this effort to make to deliver electronically papers, at least to these physics journals. I have to say, back in 1986, I started a journal called Complex Systems, which is still prospering today. Back in those days, I was sort of the first journal that had where its instructions to contributors said things like, you can send this, your paper to us by email through BitNet or UUNet or whatever else, or UUCP rather, strange email addresses with exclamation marks in them and so on. Or you can send your paper to us on floppy disks, and you can send it in TROF, or you can send it in this, you can send it in that. And I think this led the then editor of Nature magazine, John Maddox, to write a little editorial called What is an Electronic Journal, talking about my journal and being super amused by the fact that it said things like, you can send a floppy disk to us and so on. It's like, that's a thing from the distant future for that time. Now, of course, the embarrassing part of this was that 25 years later, we realized we hadn't updated the instructions for contributors. Maybe it wasn't as much as 25 years, but many years later, we hadn't updated the instructions for contributors for the Complex Systems Journal. So it still talked about floppy disks, even though by that time we were getting close to the moment when kids would say, when you show them a floppy disk, is that a 3D printout of the save icon? And had no idea what it was. But in any case, that's just the way that those things go. But when we look at sort of the flow of this idea of journals and the idea of papers and math and so on, the big thing that hasn't happened that I've been wanting to get to generally happen for 30 years, more than 30 years, is this idea of using notebooks and using computable, having computational language mixed with natural language and math language in papers, and really being able to compute from papers. And what really makes that possible is our Wolfram language effort and the fact that it is a computational language, not a programming language aimed at telling a computer in detail what to do, but a computational language aimed at explaining ideas computationally. And as such, it's something that's intended for humans to read and for computers to read, and a way to have the computer generate material that you get to put in your paper and so on. And I've been pushing for a number of years now this concept of computational essays as a way to sort of present material where you can not only read the text in English, but you can read the computational language, you can read the math, and you can run the computational language part. And if the math is a piece that is kind of done in, for example, standard form in Wolfram language, it's something that, again, you can actually have as something that you can compute with. And certainly the things I've been writing about our physics project and all the other things I write about, they all have click to copy. Any picture you see, you click it, and it'll give you the code, the computational language code that will reproduce that picture. That is really valuable. And we can see that in the development of our physics project, for example. We can see how people are routinely just building on the things that have already been done. And that's possible because there's computational language there that one can go and just take and use. And it's also important that sometimes when you're explaining something, well, you could write a bunch of words and this and that and the other. You could write maybe some mathematical notation, but you can also write computational language. And that's a unique representation of sort of the computational way of saying what you want to say. So, the way I see it is the future of things like mathematical papers and so on. Eventually, the future will be notebooks and computational notebooks and computable documents and so on, or effectively computational essays. That eventually has taken a very, very, very long time to arrive. I mean, I started thinking about those kinds of ideas probably in the early 1980s, and seriously when we released, well, when we were going to release Mathematica, probably 1987 or so, really locked in on that idea. And Theo Gray was the person in our team who really developed this notebook concept originally as kind of this, what does it do when you match, sort of word processor-like technology with computational processing? Well, you end up with a notebook. And in fact, the details of what we invented with cell groups and closed cells and all that kind of thing, that's now a third of a century old. That's something where, the people have been producing notebook-based technical documents for a third of a century. I think the very first one that I saw produced by an outside person and published in a journal was by a chap who was at that time at Apple. Oh gosh, I wish I could remember. Maybe Malcolm Slaney, if I remember correctly. I apologize if I have that name wrong. Maybe I have that name wrong, sorry. Was a notebook describing a model of the cochlea, the human cochlea. You can kind of guess at that time why it might have been interesting, I don't know, to engineers at Apple. But it was sort of the first outside notebook technical paper published in some IEEE journal in paper form, and then there was a notebook version of it. But that was a third of a century ago. And why hasn't this become more common? Well, I think it probably hasn't become more common because people think it's hard enough to get the words strung together so somebody can read them. But if we actually have to have computational language there, by golly, it's got to actually run, and people can tell if it runs or not. Well, you can view that as, people say, well, peer review is this amazing thing because it sort of validates the sort of something about papers. I'm not sure if it really does, but that's at least a view of it. Well, gosh, if you had computational language in papers, that's self-validating at some level because it's an easy sort of QA test. Does it run? Does it not run? Does it produce what the paper says it produces? So there's a certain level, it's kind of like a kind of automatic sort of quality control, better than peer review, but it's something where stepping up to that, I know when I write things, I'm putting code in there. Sometimes I get people to help me kind of clean up the details of how it works for one reason or another. But basically, I'm putting in code so that every picture that I put in a document I write has code behind it, has computational language behind it. And I know it takes a certain amount of effort to do that and make sure that it works. The main issue for me is making sure it works standalone and doesn't have any dependencies that aren't included with it and so on. But it's not terribly difficult in Wolfram language. It will be exceptionally difficult if you were doing that in a programming language, because to get to the point where you can actually write about something that you probably care about, that isn't just about programming itself, you'd have to have this whole stack of other kinds of things included, which in Wolfram language are just part of the language, but otherwise you'd have to have this library and that library, and oh, are the libraries compatible? And oh, what if the libraries were incompatible with the thing that's already on your machine? It's kind of a horrifying morass of stuff. But with Wolfram language, this kind of idea of computational language is that you can just put those kinds of things in. So what does that mean for the future of computational papers? Well, there should be a great future. We've been planning to start kind of a computational journal. We've been planning for like probably 20 years. We've been talking about doing this. We keep on not doing it. And part of the reason we don't do it, sometimes I'll run into CEOs of large publishing companies and things, and I'll point out, that few $1 billion of journal publishing that you're doing, you used to add a lot of value by doing things like typesetting and printing on paper and things like that. There's a new way to add value, which is to get people to the point where they can actually publish computational papers, where they can actually have computational language code that works and so on. But I think nobody has yet really dived into doing that. That's the future of what used to be that process of typesetting and copy editing and proofreading and all those kinds of things that used to be done and used to take real work and used to be real value added by journal publishing. That's all gone away. It should be replaced by the effort to make computational code, computational language in papers actually work. That would be a very valuable thing, very useful for people who want to build on, to do what people in academic science sort of imagine is the thing one does, which is to take paper A and build on it paper B and build on that paper C. That's kind of the whole idea of sort of the academic enterprise and the chains of citations and all those kinds of things, is to do that. But right now, we're technologically a third of a century behind, because it is not a routine thing yet to actually use computational language, which is what would allow you to do that kind of progressive building in an efficient way. And eventually that will happen. It's taken a remarkably long time. It's also worth remembering or thinking a little bit about the role of sort of publishing and what kinds of things people publish. The early journals were things like Proceedings of the Royal Society from the 1600s. People like Edmund Halley and so on were big in the introduction of the Royal Society and the Proceedings of the Royal Society and so on. I have some early copies of the Proceedings of the Royal Society. That some of it is written in English, some of it is in Latin. It's whichever. I think it's mostly in English actually. But what's interesting about it is, if you read those documents, they mostly read like blog posts today. They're kind of informal. They kind of explain, roughly what's going on. They give a little bit of, sometimes they even give a certain amount of, like the natural history ones and things, will give some kind of color about, I found the bird. It was chasing its tail or whatever, and there'll be a story around it. It won't just be the pure, a specimen of Latin name was found in a I don't know what the appropriate Latin version of chasing its tail would be, but a very formalized version of that would be what you would see today. And a lot of papers in a lot of fields, it varies with field a bit, the conventions vary with field, but one of the things that is typical of academic papers today is not very much contextualization of why are you doing this. Sort of the joke version will be, recently Smith and Jones have done X. We are going to do X plus a tiny bit. And, then you have to go back and look at what Smith and Jones did if you want the context, and you might have to go back many, many layers to get that context. In the earlier history of this kind of thing, the early kind of journal papers, they were like, really what was happening was there was some meeting of the Royal Society and somebody would stand up and talk about this or that, and that would turn into a paper read to the Royal Society, and that would have a certain informality, which makes it a lot more readable and a lot more contextualizable. And I think it's sort of a shame that stuff has gone away, and that to be sort of academically respectable, there's an expectation that you have this very, very dry form that kind of loses all of the narrative that I think is super useful often in understanding what's going on. Now, I would say something I haven't seen, people have asked me, we've done a lot of live streaming of a lot of both scientific work and technological development and so on, but particularly scientific work. And people have asked me, should everybody be doing this? Should universities routinely be doing this? And so on. I think it's an interesting possibility, because one of the things that I hadn't really internalized properly, but it's come up particularly at our summer schools and things like that, is people say, I want to understand, you wrote such and such a thing in this document. Okay, why did you write that? Well, we've exposed enough material that you really can tell. In other words, you can go and you look at the working notebook that's associated with that, and you can see what the steps were, and then you can look at the live stream where that was discussed, or even the much more extreme sort of piece of personal eccentricity, I suppose, of mine, are these video work logs that I'm producing, where literally I'm just sitting down to work and I set screen recording on and I'm recording everything I'm doing. I've never looked at them again. but we're putting those on the web. And probably the things I wrote last night, I probably spent 4 or 5 hours doing something last night, and all of that is screen recorded. And so if one ever wanted to know this particular sentence, what on earth was he talking about in that particular sentence? Well, you can go back and see what was happening. Where did that sentence really come from? You actually know the full provenance. And that's something that is, modern technology has given us that opportunity. So that's another level. That's kind of the where did it come from question. The computational essay, that's a more where is it going to type question. And that's the issue of, and one of the things that's great about Wolfram language and the way one can do things is because there's sort of small fragments of computational language. They're both things humans can read, and you can contextlessly, you can just pick up that lump of Wolfram language, put it in a notebook, run it, it'll produce the picture you want it to produce. There's no, oh, I have to load this library and do this, that, and the other. It's just the person, just like one would expect if one had defined things properly, that one has a piece of English that would be in the introduction or something that one could just sort of pick up and understand without knowing everything around it. So that's a long long description of I've almost lost track of what the original question was. Oh yeah, it was about workflow for math papers. And I think my main comment there would be that this computational language piece is an important piece. Now, I make one more, that's a general statement about scientific documents. I'll make one slightly more specific comment about math in particular. A thing that people are thinking about is the formalization of math at the level that there's sort of math one does to compute things, and there's math one does to prove things. And there's, in sort of the way that one thinks about math, in the history of math, vastly more math has been done to compute things than has been done to prove things. The idea of math based on proof as well, Euclid had that idea back in antiquity, and the kind of let's make proofs, I would say, really got kind of a, it was happening in this, even Newton modeled his Principia Mathematica after Euclid. And so that was kind of a motif for presenting these, although he was mostly presenting physics there, but he presented some mathematics as well. But then this kind of idea that math is all about proof is something that is sort of a characteristic feature of pure mathematics. It's perhaps a reason why experimental mathematics has been as comparatively invisible as it has, is because the main kind of what you do in pure mathematics is you state a theorem and you give its proof. And the proof is kind of, there's more juice to the proof than just saying, oh, I can, trust me, it's true type thing. In a good proof, the proof is the exposition of what's going on. Now, in modern times, we also have automated proofs. A surprising thing, there are automated proofs that people do, and particularly they're useful for things like automated proofs of protocols and correctness of programs and things like that. But when it comes to math, a surprising fact is that I don't believe that I believe there's only one example of an unexpected result in math that was found by automated theorem proving, and it was something that I found in the year 2000, which is this minimal axiom system for Boolean algebra, which is surprising, unexpected, and I found it completely with automated theorem proving. And one feature of that proof is it's a big, long, complicated proof generated by a machine and utterly incomprehensible to people and not useful as a piece of communication. But in any case, one of the things that people are now talking about is, insofar as the practice of pure mathematics is about the presentation of proofs, can we maybe present those proofs in more of a computational language type style as something where you can systematically build on pieces of proofs? Okay, so I think the thing that tends to get missed there is, to make that useful and usable, you have to do a bunch of language design. In other words, you need to say, oh, we've got this thing and it's a graph. What does it actually mean that it's a graph? How is it actually set up? What is its notation? How does it work? That's an important piece. And that's a piece that is this strange art, science of language design that I personally have been very involved in now for 40 years. And it's a very language design. I do a bunch of things. I think some of the things I do are quite intellectually difficult. I think the one that is the pinnacle of intellectual difficulty is language design. And there's a reason for that, because language design is really about how do you take ideas and crispen them to the maximum extent? How do you really understand the essence of ideas in a certain way? And so language design is hard. And a big piece of what's necessary in successful formalization of proof style mathematics is language design. We tried about 6 or 7 years ago, we had quite an initiative to try to get mathematicians and so on to help define that language for pure mathematics. I think in Wolfram language, we maybe have 7,000 primitive constructs at this point. I think with another 1,000 to 1,500, we would cover sort of all of standard current pure mathematics. But what those 1,000 or 1,500 primitives really should be, that's a lot of work to figure out, a lot of judgment, a lot of language design, a lot of understanding the essence of things. It's difficult stuff. And we tried to kind of get that to be something that will be a thing in the mathematics community. And although we have many friends in the mathematics community and people use that technology all the time, people didn't really care very much. It wasn't something where people were saying, oh, we're pure mathematicians, we would really like this to pursue our art. And actually in recent times, as I've understood more about metamathematics and about foundations of math, and there'll be something I'll be talking about a bunch more in a few weeks, I hope, I've sort of understood why this is, that this drive towards axiomatization that people like Hilbert were really pushing 100 years ago or so is a drive in a direction of mathematics that is a different direction than what most pure mathematicians think they're doing. For most pure mathematicians, they're drawing in brush strokes. The analogy that I have is the level of axiomatic mathematics, of grinding through specific axioms and proofs and so on, is like molecular dynamics. It's like a bunch of molecules bouncing around in a gas. The level of mathematics that's done by a working human pure mathematician is more at the level of fluid mechanics, the big brush strokes, not the precise details of where every bristle of every brush went and precisely how was it arranged. And so that's, in any case, but the concept that's arisen is this notion of not automated theorem proving, where you say, here's a theorem, now go generate the proof, but more proof assistance, where what you're saying is, I'm going to produce these pieces of sort of asserted to be true things in mathematics. Now let me put together the puzzle, build up the tower based on those sort of Lego pieces or something to get to the thing that I want to get to. And so this is the idea of proof assistance. And sometimes they'll have a sort of auto suggestions that might be even based on some automated theorem proving, or might be based on calling Mathematica or something to say, what is the thing that I should add next, so to speak. But that's kind of an idea for how to build up kind of a formalized structure of mathematics. Is this the future of mathematics? I'm skeptical. I think that it's an interesting thing to do. It's been most useful in areas like protocol verification and things like that, in the sort of more computational areas. There are certainly cases where, Tom Hales, when he was proving the Kepler conjecture, people didn't believe his proof. He made quite a lot of use of our technology in his proof, it's a surprisingly complicated proof of a claim that Kepler had made that the closest packing of spheres is the standard packing that you see of fruit in grocery stores, so to speak. That had been never proved, and Tom Hales came up with a proof, but then it was a big long paper, and the mathematics community was like, oh, we don't understand this. Are you sure you really got it right? And he basically said, no, I'm going to make a proof assistant. He spent a decade doing that. Make a proof assistant system which can actually brick by brick establish that this thing is definitively and firmly true. But I'm not sure how much, what do we learn from this? It's better than automated proof in the sense that it was a human constructed thing, and it does presumably tell some kind of story, but it's a story that has been, it's not a story that seems to be as useful as one might hope. So, that's another direction for kind of the sort of the future of presentation of math is this idea of the kind of formalized proof. I personally think that, in the efforts that we've made to build Wolfram language and make it a computational language that's good for humans to read, that's a critical idea. If you really want humans to read computational stuff, you've got to do the art of the thing as well to make it so that that's something that has humans can really, where there's sort of clarity of exposition is part of the design of the system. And I'm not sure that that's been understood yet in the case of kind of the proof assistant world, but I think that's a necessary piece. Whether that is the correct way to think about the foundations of mathematics, whether that's a correct way to think about kind of how progress should really be made in mathematics, that's a different question. I'll probably have more to say about that in a few weeks, because I've been working quite actively on kind of mathematics and the foundations of mathematics. All right, unfortunately, I'm really late. There's one question here I'm going to address from John. How can we be sure that the software generating the proof is correct? Well, you see, the nice thing about automated proofs is you get kind of a proof function that is a thing where, for example, in the automated proof of the simplest axiom for Boolean algebra, the proof is basically a series of steps where you're substituting one expression into another expression, and you're just doing that hundreds of times, and eventually you get the result. Okay, so it was difficult to find that series of substitutions to do. That's the art of finding the proof. That's what the automated theorem proving system does. But once you've found the series of substitutions, any old dumb machine can go and do those substitutions. So you have, typically, you can have many different, very straightforward, differently written pieces of code that just go through and just do the substitutions. And so that's the way that you would validate the proof. And that's a straightforward thing to do. And that doesn't depend on, oh, did your automated theorem proving system, which may be a quite complicated, quite heuristic piece of code, did it hiccup at some point? Doesn't matter. Because if the series of substitutions it defines, you can run through those and validate that it's correct, and that's an easy thing to do. Hard to find the proof, easy to check the proof. It's actually the original paper on NP completeness by Stephen Cook in 1971 was actually about proofs and was about this very point, that it can be hard to make a proof, but easy to check it. All right, I think that's it for today. Tomorrow we have some other live streams about completely different topics, and look forward to seeing you all again. Another live stream. There'll be, Friday is my science and technology Q&A for kids and others. And then this time next week, we are alternating between history of science and technology and business innovation and managing life Q&A. All right, well, thanks for joining me for